Okay, here we go. So first up, we have electronegativity. I need to know my trend in electronegativity. Electronegativity increases as I go up and to the right. So now I'm just going to look at my periodic table and sort of find where all these things are relative to each other. So I see calcium over here kind of on the left, middle of the periodic table, rubidium a little bit below and to the left of that. I see sulfur over here, and arsenic is bottom, right below and to the left of sulfur. So starting from the um, looking for the lowest would be rubidium, that is the furthest down and to the left, and the highest would be sulfur. So it would be choice B. All right, what would happen if I double the volume and keep everything else constant? So if I think about P1, V1 equals P2, V2, that means P1 times V1 equals a constant. So if I double V, I'm going to have to make P a half in order for that to stay the same. When the solution feels hot, that's because energy is being released or heat is being released from the reaction, and that is an exothermic reaction. Quantum numbers. All right, all my n's are fine. Remember, they can be any number 1 or higher. They have to be a whole number. L's, I'm comparing them to my n's, and they're all fine. Remember, they can go from 0 to n minus 1. And when I look at my m sub l's, remember, they can go from negative L to positive. So there's a problem with B. It can only be 0. All the m sub s's are fine because they have to be plus or minus 1/2. And each bond is 2 electrons, so a triple bond would be 6 electrons. All right, molecular speed. If I'm looking at the same temperature but different masses, then I'm looking for the lowest molar mass. So I'm just going to quickly pull out my periodic table and figure out these molar masses. Some of these I already know because I'm familiar, but you might have to look them all up. But anyway, so methane's about 16. Krypton looks like it's around 84. Nitrogen is around 28 because it's N2. Carbon dioxide is around 44, and argon is about 40. So the lightest one would be the fastest, and that is methane CH4. Converting pressures, I do have the conversion factors available that I'll need for this. So I'm going from millimeters of mercury to kilopascals. So if I pull out my list here, I can find millimeters of mercury converted to pascals. I'm going to go ahead and convert it in my head, divide by 1,000 to get kilopascals, but you could do that in a separate step also. So I'm doing 101.325, that would be kilopascals. And then I will just put that in my calculator. But again, I could do the 101,325 and then divide by 1,000 to go from pascals to kilopascals. All right, here's another speed of gases. This one's talking about the same type of molecule, but different temperatures. Higher temperature will be faster. Definition of a solution. Solvent is what we have the most of, and the solute is what we have less of. For nonpolar covalent bonds, I either need all the electronegativities, or in this case, I see one right away where it's both things are on like the same thing on both sides of the bond. So bromine-bromine bond's definitely going to be nonpolar. All right, periodic trends. So ionization energy. Ionization energy is the energy required to remove an electron. It increases as I go to the right because, of course, those want more electrons, and it increases as I go up because they're smaller and the electrons will be closer to the nucleus and more tightly held. So I'm looking at magnesium and calcium. Magnesium is higher up, so it would be higher. Or calcium and arsenic. Arsenic is to the right, so it would be higher. All right, next up, radius. Radius increases as I go down the periodic table, so I'm drawing my arrows as they increase. And it increases as I go from right to left, not left to right. So when I look at boron and aluminum, aluminum should have the higher radius. And when I look at boron and fluorine, boron should have the higher radius. And now that I'm rereading this, I see it actually says smaller radius. So let me change my answers because I was thinking larger radius. Okay. There we go. Smaller radius would be boron and then fluorine. All right. Smaller radius for ions. If I'm removing electrons, it will get smaller. And that would make it a cation. If I'm adding electrons, it will get larger. And then finally, electron affinity and electronegativity. One is how much it wants an electron in general, and the other one is how much it wants an electron within a bond. Both of those, I'm looking on the same row, calcium and bromine, so both of those increase as I go toward the right, and so bromine would have the higher of both. All right, next up, we're looking for some geometries and bond angles when I'm already given the Lewis structure. So I'm looking at number of electron groups on the central atom. This one has 2, which would be linear, and that would be 180 degrees. This one has 3, and they are all bonds. That would be trigonal planar, which is always 120 degrees. This one has 4 electron groups, 3 are bonds, so it would be trigonal pyramidal, and anytime there's 4 electron groups on the central atom, it would be 109.5. All right, now I'm looking for polar molecules. I'm looking at the ozone first. That's not going to have any polar bonds in it, so it doesn't matter what anything else looks like because they're all O's. But for the carbon dioxide and the water, it will matter. So I'm going to draw my Lewis structures starting from all single bonds. These are common ones that we've practiced, so maybe I tried to draw them on hydrogen. So maybe you already know what these look like, but if you don't, that's what I'm doing. So then I'm adding up how many electrons I'm supposed to have. My water is already fine, but my carbon dioxide is supposed to have 16, and it actually has 20. So I'll put in some double bonds. So geometry-wise, that would be linear on the left for carbon dioxide and bent for water. The linear means that the bonds would cancel. They are polar, but they would cancel, so that would be a nonpolar molecule. But in my bent molecule, overall, they would not. I'm actually drawing my arrows in the wrong direction. Oxygen's more electronegative, but it doesn't matter. What I can tell is that overall there is a polarity here. And so water is my polar molecule. All right, next up, converting wavelength to frequency and energy. I need to know these equations. The constants are available on my equation sheet, but not the equations. So C equals lambda times nu. I'm going to solve that for nu, the frequency, by dividing both sides by lambda. I can get the speed of light from my equation sheet. It rounds to about 3 times 10 to the 8th meters per second. Since that's in meters per second, I've got my wavelength to plug in, but I do need to make sure it's in nanometers. There is a conversion on here. It says 10 to the negative 9th for nano. That's how many base units are in one prefix unit. That's not how I usually do my conversion, but it is on there if you need it. I would say there's 1 times 10 to the positive 9 nanometers per 1 meter. That was saying 1 times 10 to the negative 9 meters per 1 nanometer. Either way, you'd get the same answer. And that is 9.4 times 10 to the minus 7th. And I can divide that. My units would be 1 over seconds or hertz. To 2 sig figs, I get 3.2 times 10 to the 14th. All right, for energy, I can look up Planck's constant. That's another constant on my equation sheet. It's 6.626 times 10 to the minus 34th joules times seconds. And then plug in the frequency that I got. I'm going to write 1 over seconds this time just so I can see that the seconds cancel. So this will be an answer in joules. All right, looking for an error in a Lewis structure. The 2 things I'm going to check are that the octet is complete on everything, which looks correct, and then the total number of electrons, which is 11, and I actually have 12. So in order to draw a corrected Lewis structure, I need to erase one. I would remove it from the nitrogen, and now everything has a formal charge of 0. All right, in this one, I do not have a complete octet on everything. Nitrogen's missing electrons, hydrogen, one of those has 2 bonds. Like, I've got issues all over the place. So I've got a nitrogen and oxygen, and I got to put these 3 hydrogens in. I'm going to put it on this nitrogen because that's going to give me all formal charges of 0, but you could play around with it. I'm checking to make sure I have the right total number of electrons. I should on 3 hydrogens, a nitrogen, and an oxygen. I counted 16, but I actually think that's wrong. I think I should have 6 plus 5 plus 1, 1, 1. That's 14. 14, and that's what my picture has. So this is the correct Lewis structure. And all formal charges of 0. All right, if you're trying to remember how to calculate formal charges, that's what we're doing in this question. So I'm going to look at how many each element has from the periodic table, -1 for every dot, -1 for every line. So sulfur is 6 minus 6 minus 1, 6 minus 3 minus 2, and 6 minus 6 minus 1. Oxygen, chlorine, sorry, is 7 minus 6 minus 1, 7 minus 6 minus 1. All right, so I'm going through these fast, but it's the number from the periodic table, -1 for every dot, 1 for every line. All right, so then the ones and the negative ones are out. I want one of these other ones where they have some zeros in there. And now I have to pick, oxygen is more electronegative, so it should get the negative formal charge. All right, so that's my answer. And then it says how you arrived at your conclusion. So I'm looking for the one with the lowest overall formal charges, which would be either of the 2 on the left. And then I'm picking the one in the middle because the negative formal charge is on the most electronegative element. All right, and if I went through formal charge too fast for you, so again, this would be 6 for oxygen minus 6 dots minus 1 line, 6 dots, 1 line, 4 dots, 2 lines. Chlorine is 7 minus 3 minus 2 plus 2, and hydrogen is 1 minus 1. All right, I'm looking for just a property of a gas, so I'm going to use the ideal gas law, PV equals nRT. I'm solving for pressure by dividing by volume, and now I'm just going to plug everything in the correct units. The gas constant is on my equation sheet. Remember, I want the one that has liters, atmospheres per mole Kelvin. There are 2 versions of R. We will use the other one, maybe not in this class, but in the next class. So make sure you're choosing the correct one. We do not want the one with joules in it here. We want the one with liters and atmospheres. Temperature needs to be in Kelvin, so 47 plus 273. And put this in my calculator. Get an error message. But not because I'm doing the problem wrong. I don't know what that was. I'm trying to figure out if I'm still recording. It looks like I am still recording. So, okay. All right. Whew. 17.7. And then looking at my units, moles cancel, liters cancel, Kelvin cancels. So my units would be atmospheres. Okay, change in enthalpy based on bond energy data. It is bonds broken minus bonds made. So I do need Lewis structures. I'm going to just write those quickly because we've done some of these before. But carbon monoxide has a triple bond. Oxygen has a double bond. Carbon dioxide is double bonds. I'm drawing one for every molecule stoichiometrically. So because there's 2 carbon monoxides, I'm drawing it twice. You don't have to do that, but that's what I'm doing. And then 2 carbon dioxides, I'm doing that twice. I just want to make sure I carefully count all my bonds. So I'm going to break all the bonds on the reactant side. which is 2 carbon-oxygen triple bonds. And then I've got 1 oxygen-oxygen double bond. And then I need to subtract the ones I'm going to make. I'm going to take all those atoms and rearrange them into CO2s, which has 4 carbon-oxygen double bonds. All right, multiply by 2. All right, and I get negative 557. And my units from my bond energies are kilojoules per mole. All right, now I need to draw the Lewis structures, and then it's also asking me for geometry and bond angle. So I'm going to attach everything to the carbon, count up how many electrons I should have. This looks perfect as is. 4 electron groups, all bonds, that's tetrahedral. 4 electron groups is 109.5 degrees. NO3 minus, I'm going to attach everything with single bonds, complete the octet on everything. Count up how many electrons I should have. Nitrogen is 5, oxygen 18, 1 negative sign, so I should have a total of 24. I actually have 26, so I'm going to put in 1 double bond. That leaves me with 3 electron groups on the central atom. Any bond is an electron group. And so that's trigonal planar and 120 degrees. All right, next NOCl, complete the octet on everything. Count them up, 5, 6, 7, so 18. I actually have 20, so I'll put in a double bond. Okay, I don't like this because it doesn't have good formal charges. I see nitrogen has 6 electrons, like 6 things. It would be a +1, and oxygen is a -1. And when I look, I actually should have put nitrogen in the middle. Like nitrogen was less electronegative, so I'm just going to flip-flop them, keep everything else the same. And now I do have all formal charges of 0. Either way, I end up with bent for my geometry and 120 degree bond angle because there are 3 electron groups, but this is the better Lewis structure. And then finally, water, we did that one earlier. It would be bent, and this one has 4 electron groups on the central atom, so it would be 109.5 degree bond angle for water. All right, calculating enthalpy from the delta H of formations, I would do products minus reactants, and this is all stoichiometry of 1, so my products would be calcium oxide, negative 635.6, CO2, negative 393.5, and that's it for my products, and then subtract off my reactants, which is just the calcium carbonate. Just being really careful with my signs here. And I get 177.8. And that would come, the unit would come from my delta H's, which were kilojoules per mole. This is a positive answer, so it is endothermic. Remember, negative means negative is exothermic, positive is endothermic. Okay, last but not least, I have a volume, a temperature, and a pressure, and then I'm changing the temperature, and my negative sign got on the wrong line, so negative. Okay, so I'm changing the temperature and the pressure. I can write my own sort of reduced gas law. Let me start from the ideal, not this. Let me start from the ideal gas law. PV equals nRT, and think about what's going to stay constant in this, and it's going to be the number of moles of gas and R. Those are my constants, so I'll solve for those by themselves. And so it's PV over T equals a constant, so then I can do P1 V1 over T1 equals P2 V2 over T2. I'm looking for an answer that's a volume, so I'll solve for V2 by itself by multiplying both sides by T2 over P2. All right, so let me see what I've got. I've got a V1, I've got my T1 here, which is, I'm going to convert it to Kelvin because I'm going to need it to be in Kelvin. Remember, in gases, they have to be in Kelvin. 301.5. This will be my P1 here. And then my P2. So it's negative 34.35. For my T2, I'm going to convert that to Kelvin. I get 238.65. And that's my P2. And then I just plug it all in carefully in the right place, right? So T2 goes first. I mean, on top. Doesn't matter what order, but P1 is 757.2. The millimeters of mercury is fine, just Kelvin has to be, temperature has to be in Kelvin. As long as the pressure units cancel, they'll be fine. And they're both in millimeters of mercury, so that's good. All right, I'm ready to put this in my calculator then. And I get 10.2. My units would be, Kelvin cancels, millimeters of mercury cancels. My units would be liters, and I was looking for a volume. So I'm good.